Hello everyone, my name is Jack Jorgensen. I'm a PhD student in the Department of Mechanical Engineering at the University of Western Australia in Perth. I'd like to introduce the paper I'll be presenting at OME 2022 entitled Probabilistic Assessment of the Effect of Bolt Preload Loss Over Time in Offshore Wind Turbine Bolted Ring Flanges using a Gaussian Process Surrogate Model. I co-authored this paper with my PhD supervisors, Professor Melinda Hodkiewicz, Dr. Edward Cripps, and Dr. Ghulam Mubashir Hassan. I'll provide a brief overview of the paper. If you'd like to hear more, please come along to my talk at the conference in June. In this work, we are particularly interested in the fatigue assessment of bolted ring flange connections in the offshore wind turbine structure. On the right is shown a breakdown of some locations within the structure where major bolted ring flange connections are located. Increasingly, the connections between the monopile foundation and the transition piece, on the furthest right, is being made with bolted ring flanges. On the left, a schematic of an approach termed the segment model, used to analyze the loads in the bolted ring flange by focusing on the maximally loaded bolt. The transfer of the tower shell load, Fz, to the bolt load, Fb, is a complex and non-linear relation, dependent on a number of factors, including the bolt preload. Computationally efficient analytical techniques may be used to analyze this load transfer. Conversely, more complex and computationally expensive FEM simulators may also be used. One of the primary concerns when designing the overall offshore wind turbine structure, and the bolted ring flange in particular, is the fatigue lifetime, with up to 1 billion load cycles possible across the lifetime of operation. The preload of the bolts within these connections has a material impact on the achieved fatigue lifetime. There is uncertainty on the achieved preloading of bolts on physical structures. This uncertainty is acknowledged formally in the 2021 edition of a leading design standard, DNV ST 0126, which states the assembly preload of a single bolt may be considered as a normally distributed random variable. Different methods of preloading result in different levels of uncertainty. For example, torque-based methods may be expected to return a higher level of uncertainty than tension-based methods, according to the NASA standard 5020B on requirements for threaded fastening systems in spaceflight hardware. See the table on the right based on this NASA standard. Furthermore, the preload for bolts may reduce over time, over both the short and long term. These uncertainties should be considered in design under the fatigue limit state. This is straightforward using the analytical methods covered, but becomes computationally impractical if the FEM simulator to represent load transfer behavior is used. To assess the influence of variation in bolt preload on the fatigue limit state, a probabilistic analysis may be performed. Given the necessity to simulate numerous scenarios in such a probabilistic analysis, this is even further out of reach for computationally expensive simulation methods. We use the approach of structural liability analysis in this work and undertake this using a Gaussian Process Surrogate Model to emulate the computationally expensive FEM simulator. This is compared to the standardized analytical approaches. The Gaussian Process Surrogate Model is computationally efficient and leverages the complexity encoded in the FEM simulator. The general methodology used in this paper is shown here and summarized as follows. The specific bolted ring flange under investigation is defined, including dimensions and the tower shell load profile. An FEM simulation model is constructed to model the transfer of tower shell load to bolt load. A Gaussian Process Surrogate Model is then trained on a limited subset of results from the FEM simulator to emulate the transfer function between the tower shell and bolt load. See reference 6 for a background. A set of bolt preload samples are drawn from the defined distribution of the bolt preload, assuming the preload is a normally distributed random variable. These samples are used to perform a Monte Carlo simulation for the fatigue limit state. Fatigue damage under a bolt preload sample is calculated using the bolt stress profile predicted with the Gaussian Process Surrogate Model, and using a minus sum of the cumulative fatigue damage. The calculated cumulative fatigue damage is assessed in the limit state G against the fatigue resistance, itself a random log-normally distributed variable. The probability of failure and reliability index under the fatigue limit state is estimated over the full set of Monte Carlo iterations. The estimated probability of failure is compared against a target value defined in design standards such as DNV ST0126. This methodology is then repeated over time, where the distribution of bolt preload is expected to vary. Reassessing the structural reliability upon observations of installed and operational bolt preload allows assessment of the impact of this variation in preload. An example analysis using the bolt preload distribution assumed during design is shown in the plot. 200,000 Monte Carlo iterations are presented to estimate the probability of failure under the fatigue limit state. The allowable fatigue damage samples are shown by the blue markers, plotted against the corresponding bolt preload samples, noting that the allowable fatigue damage is not dependent on the preload. The calculated cumulative fatigue damage sample using the GP Surrogate Model approach, emulating the FEM simulator, are shown in red. These are plotted against the bolt preload sample selected. The calculated cumulative fatigue damage sample using the simplified analytical Schmidt-Neuper method are shown in green. These are plotted against the bolt preload sample selected. The probability of failure under the fatigue limit state can be estimated by calculating how many samples of the cumulative fatigue damage are higher than the corresponding sample of allowable fatigue damage. In this paper, we repeat this analysis for varying assumptions of distribution of bolt preload to mimic the expectation of variation in operation. Methods to account for maintenance action, principally bolt preload retightening, are also covered. Thank you for listening. If you'd like to hear more detail about the work, please come along to the conference session on offshore wind, fatigue and structural analysis, session 090113 in Hamburg in June. My contact details are shown here and a short set of references are provided. The full references can be found in the paper. I look forward to presenting in person in Hamburg.